Okay,
So,
let's see.
Andy, we were going to ask everybody to turn off video during this so that her audio comes through a little better.
Yes. That is an excellent point. So if you have video on, if you can flip it off, at least for the keynote, that would be helpful just in case. And mute microphones as well.
Okay, so what everyone should be seeing is the title slide of my talk. So can everyone hear me, number one?
Yes, ma'am.
Okay, and then I have my video on. I can't see myself, so I'm hoping that I'm in the frame okay. I'm standing because I like to stand when I give talks. So hopefully you can see me. And then I'm sharing my screen and I'm recording. So we should be good, right, Stefik?
I think all of those things are coming through, yes.
Okay, very good. And then the last thing I want to do is get my chat box up so I can see. I will be monitoring the chat box in case there's quick questions or something, but of course at the end I'll leave plenty of time for questions as well. So thanks very much for the intro. Thanks for hanging with us this morning. I'm excited to be here. The title of my talk is Good Vibrations, Multimodal Graphics on Touchscreens for Increased Digital Access. As Andy had mentioned, my name is Jenna Gorlewicz. I'm an associate professor at St. Louis University in mechanical engineering, and most of my time is spent in the area of haptics and human-machine interfaces. So excited to be here, and please feel free to take note and make note of any questions that you have. Happy to have a conversation at the end. So first things first, let's see, I have a clicker. Is it going to work? Maybe not. There we go. I know this always happens. I work in the area of vibrations, and titles go really well when I say things like good vibrations, but then everyone starts singing Beach Boys, Good Vibrations. So just to be clear, that's not what we're talking about today, okay? So as much as that's a great song, we're not talking about the Beach Boys or their hit Good Vibrations. But how I would like to start today is think of some of the technologies you've used just in the last 24 hours. And if you can, type some of them in the chat window, or if you want to turn your mic on for a minute and sort of voice them or shout them out. Just think of some of the technologies you've used. What are they? Computer, iPad, cell phone, remarkable, phone, iPad, laptop, vacuum cleaner. I need to use that. Computer, phone, various apps. So we see a theme, right? Coffee maker. So some folks are branching out into sort of the appliances or some things that we use in our home. But many of us on a regular basis use screen-based medium, whether it's a computer, it's a phone, it's a tablet. But the really interesting part of this is how many of them use touch? Voltmeter, nice, Tim. So when you really think about it, if you think about the technologies that you use, so of course you have to like push a vacuum cleaner, or if you're using the microwave that Pranav was talking about, it's ultra screen based, or if you're using your tablet, there's some element of touch, but it's very artificial, right? So it's kind of funny that touch screens are called touch screens. They're more like touchable surfaces. Right, the true touch interaction that happens is very, very limited. And this is sort of a trend in technology. Current technologies have really inhibited our human haptic capacities. So think about it. And then we're experiencing this now for other reasons outside of just technology alone. But instead of reaching out and shaking hands, which people did so often, we now hop on Zoom and we see each other and we say, hi, how's it going? Right, but it's kind of not the same. Instead of giving high fives or, great job, celebrating, we can like send emojis that are, mimicking a high five, but not in any tangible way. And even in education, right? We've seen this shift. Instead of sitting in the lab and tangibly doing things and physically manipulating objects, we have all kinds of simulations. And that's not to say that anything on the bottom or on the tech side, the emojis, the Zoom, the online sims, that's not to say that those are bad, right? But it is to say that it is significantly lacking in the touch space. And our current situation has not helped this, right? So with the situation that we have going on with the pandemic, we're asked to social distance. We're asked to keep to ourselves. And this is really unhuman, right? Touch is one of our earliest ways of learning. As a child, what babies do is they pick things up, they put it in their mouth, they feel all the sides, they grab your face, they pull your hair, and they learn, right? We learn through touch, and we connect through touch. It's one of the most intuitive forms of being human and experiencing the world around us. And so what I like to think about is, why is the haptic channel tertiary at best in technology? Right? All of these technologies that have come out require extensive visual loads. And the haptic channel kind of gets this rap of sort of being a secondary channel. Like, maybe we'll send you an alert or a notification through it. And this is sort of despite really cool advances in the haptic space. So if you look at touch technology advances, and this slide is by no means exhaustive, but what I'm showing on this slide is some pictures, and I'll go through each one just briefly. Pictures of various sort of wearable and portable haptic interfaces that relay really cool touch feedback. So the image in the upper left is a wearable sleeve. This is without all the coverings on, so the insides can be seen, but it has various motors that enable pressure, thermal feedback, tactile feedback, and it can go up and down all of the arm. And then there's things like this wearable vest that are meant to like simulate hugs. Okay, there's wearable armbands that can do everything from squeeze, vibrate, and provide kinesthetic feedback. And even in the touch space, there's been a lot of work looking at surface haptics, or what we call surface haptics, which is this notion of sort of conveying sensations of friction, or enabling people to perceive friction on screen, so that you can feel things like textures. So something feels bumpy or smooth or sticky or slippery. And then there's been a lot of work looking at devices that can give force feedback to the user's hands or arms to provide even a sort of a more realistic touch interaction. We have all of these advances in touch, but there's so many challenges associated with sort of integrating it within mainstream technology. So one is, it costs a lot of money. And that's partially because in order to do rich touch feedback, there's usually hardware associated with it. And then that leads into, there's usually another device or an add-on or something else that you have to carry around. And we already have so many devices, right? So do we really want to carry another one? And then there's an element of, we just want it to work, right? Like, we just want it to be human. We want it to feel natural. And so that easy button hasn't been there yet for touch feedback. But this lack of rich touch interactions in technology is detrimental. And it's detrimental on a lot of fronts. It's detrimental in just the way we communicate with one another. It's detrimental in the way we access information. And it's also really detrimental in education. And so now more than ever, but as electronic content moves, as educational content moves to the digital space, this problem is growing, right? And it's particularly problematic in science, technology, engineering, and math, where concepts are often very visual. And now we're asking students to engage via visual platforms and visual technologies. And so we've all seen things like this, right? We've seen chemistry diagrams, we've seen science diagrams, we've seen math diagrams, we've seen tables, we've seen charts, we've seen diagrams. STEM content is, and it continues to be, highly visual. The visual bias is only growing, and the technologies that we have are only making it worse, right? And so a lot of the work that I focus on in my lab is, how do we get past this? How do we bring touch back in a meaningful way in technology? And we know what tools are being used today to convey graphics through touch, right? There's one of the things that I'm always amazed by when I work with teachers of the visually impaired, special ed teachers, is their creativity. Because they can come up with something on a dime that's going to work, and it will work. And it's usually simple, and it's great. Okay, so we have things like swell paper, we have cork boards, push pins, rubber bands, there's wiki sticks, there's embossed graphics and tactile graphics. But what happens in the digital space is it's so much more challenging, right? Because all of a sudden I don't have a copy of this graphic, it's just there on a screen and I need to do something about it. And so there's really two ways to access it. One is if you have the graphic ahead of time and you can prepare it and make a tactile graphic, that's great. Right? Or what we see sometimes is like alt tags or captions, you know, that'll say, okay, if this is a diagram of a flower, the flower parts involved, blah, 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 blah. Okay, but we still know that like a picture is worth 1,000 words, right? And none of the alt tags, if they exist, have 1,000 words. So they don't do justice. And the tactile graphic is probably the best form because I can put both of my hands on it and quickly explore it. But I have to have that. Like I have to have it prepared and it has to be printed and there for me in advance. And so what we're really interested in is sort of this notion of readily available, refreshable, real-time display of graphics digitally. And there's been lots of extensive work sort of looking at this idea. Our approach has been sort of the caveat of with devices that people are already using. And so there's pluses and minuses to doing that. The advantages are the potential for adoption and widespread use is larger because we're using hardware and devices that are already being used, right? The downside is we're inevitably going to be limited on our hardware capabilities. And so the platform that we're looking at to do this is touchscreens. And the reason is because it has the visual display, it has the ability to play sounds through embedded speakers, and they have the ability to vibrate. Is vibration the best form of touch feedback out there? No. Is it the most mainstream? Yes. Can we do more than what we're doing right now with vibrations? We believe so. Why touchscreens? Because they're everywhere, right? We all have, or in some capacity have used, or maybe have experienced access to a touchscreen in some form or another, and they're becoming embedded in more and more of our devices. And so what we like to think about is, what if graphics could be more than just a visual representation, right? What if they did something like this? Like what if they could have embedded characteristics where they had a tactile component and they had a sound component embedded? So a pie chart, I'm showing a pie chart, it has 3 segments. What if the borders made sounds and the different pieces of the pie, you know, it could voice aloud the percentages and maybe there was a vibration, a distinct vibration associated with each section. Or similarly for a bar chart, what if the axes and the grid lines made sounds and the bars each had distinct vibrations that represented categories? Or you could switch that up with sounds and vibrations, they're somewhat interchangeable. Same with sort of line charts or scatter plots. What if we could embed these multimodal sort of identities into the features of graphics? And the whole purpose is not to replace tactile graphics, for example, or to replace any of the other things. The purpose is to raise the bar for what's considered accessible for graphics digitally. Like if you're walking around or you're browsing on your your tablet and you come across a graphic, what can we do in the here and now to make that thing more accessible than what it is? So that's what we spent roughly the last 8 or so years looking at. And we've really kind of tackled this problem from 3 areas. So the first question was, is this even possible? Like, can vibrations be used in a way that is meaningful like this? And so our initial investigation sort of centered around just basic graphical elements, points, lines, shapes. And then once we saw sort of the potential and the promise with that, we moved more into, okay, well, if we're going to do some type of digital rendering of these things, we need to have some standards and guidelines around that. And so we spent the next year sort of establishing some of these perceptually rooted guidelines. And then now we're moving into more complex static as well as dynamic content. So I'm going to just quickly walk you through some of these investigations. So the first thing we did was we looked at, can people follow lines? And we did this with various representations. So the lines were displayed on a touchscreen and we did 8 orientations of lines. And the really cool thing about doing these on touchscreens, which we love, is when we can track finger position. So we can see where people spend their time And we can sort of recreate their exploration paths and look at, were they really tracing the line? Were they not? Where did they spend their most time? So there's all kinds of interesting stuff that comes out of running these studies, just looking at how people explore these things. And we compared sort of auditory representations with vibrations, with combinations of both that have borders. And what we found was that, so there's sort of two recommendations here. One is, if you're gonna do just a single line, vibrations were preferred over sounds for tracing. If you want to do super fine tracing where you don't want to veer off the line, then borders of the alternate modality were the best performers. So for example, a line that vibrates, but then there's an auditory border around it. So if you start to go up or down, you hear that sound and you know to sort of autocorrect. And then, so what we did was we had individuals trace these various line profiles, we recorded their finger positions, and then we asked them to recreate what they felt. So did they, in their head, come up with some type of mental model of what they just traced? And what we found was that, so I'm showing this bar graph on the right, and there's sort of two categories. There's all of the orientations put into one, and then there's the orientations where the lines were only linear. They had no obstructions or no sort of bumps in the road. And the average accuracy across all lines wasn't as high as we would have liked it. It was like 62 to 73%, depending on the modality. But once we removed the extrusions, that accuracy went up to 81 to 93%. So what that told us was it's possible, but we need to do more, right? We need to do more. We need to give the user more information, especially when there's bumps in the roads or when the profiles are nonlinear. So then we moved into nonlinear lines and we investigated, how do we represent these inflection points? Now, how do we get them to understand? How do you get someone to understand that, okay, you're at the maximum or you're at the minimum and the line profile is about to change directions? And so here we did a study looking at how many inflection points are needed to sort of give users the notion of the profile of the line is changing. And so, for example, in the top figure, I'm showing the black line would vibrate as your finger's on it. And when you hit that yellow dot, you might hear a sound. And the sound scales with if it's low or high, where it is on the profile, the line profile. And then the bottom, we have more inflection points. So you can see the green and the blue. So it gives sort of a more scaled approach to the minimum or the maximum that you're approaching. And I should say that all of these studies have been done with individuals with blindness or visual impairments. And they're usually a combination of adults. So we do some work with adults, go to things like the NFB convention, and people have graciously continued to participate in our studies there. And we work with partner schools, like residential schools for the blind, where we get some children, you know, middle school, usually middle school and up. And they've also graciously let us come to their summer camp. So all of the data has come from individuals with visual impairments and blindness. And what was cool here was that there was no statistically significant difference found for either 1 point or 3 points. That didn't matter at all. But their deviations were much, much better. And they were able to trace the profiles much, much better with these inflection points. And that's really what we wanted out of this. We wanted to understand, can they follow nonlinear lines? And in fact, when we give them this additional information, they can. Okay, so now let me just move to, so what have we done? After we did those initial studies, we're like, okay, they can find points, they can follow lines. We wanted to dig in a little bit deeper. And so as a haptics researcher, one of the most interesting questions to me was, well, what are the good vibrations, right? Like, what are the most appropriate vibrations we should use? Now, there's a lot in the haptics literature on how people perceive vibrations. That already exists. We did not need to recreate the wheel there. But what we wanted to understand was, how do these vibrations map over to sort of typical tangible representations that individuals see on tactile graphics? So for example, dotted lines, dashed lines, solid lines. Is there, and if there are, can we map vibrations over that represent something similar to those? So we did another study where we played various vibrations of different frequencies, and we asked people to categorize them or tell us which one between, it doesn't feel like a line at all, it feels like a solid line, feels like a dashed line, feels like a dotted line. What does it feel like? And so what we found from that was that if you're using vibrations less than 10 hertz, those tend to be perceived as dashed lines. If it's between 10 and 25, those tend to be perceived as dotted. And if it's greater than 25, it's solid. But we have some hardware limitations that keep us from going above 100 hertz. That's just the nature of the actuators that are in the touchscreens that we're using. So that was a super interesting study. And we also looked at discrimination, because one of the things that we want to be sure of is that we're not just using 5 vibrations and they all feel the same, right? So we also saw that users best discriminate between 2.5 and 50 hertz from 10 hertz. So somewhere in that range is where we want to work. And there's much more to be done. I'm going to talk a little bit more about the vibration side in a bit. And the other thing that sort of researchers in this space tend to do, and we did the same, is we use tablets. And there's reasons that we use tablets. The hypotheses were, well, tablets have a bigger screen, so it gives you more area to explore, right? So you don't have, everything's not so condensed. The problem is that tablets are a little bit iffy with whether or not they contain vibration. The perfect example is iPads. We have been waiting forever for Apple to put vibration capabilities in their iPads, and they haven't, and they still don't have it in there, right? And so from the standpoint of widespread use, we know that iOS dominates the market, right? And we'd really like to be able to use iOS platforms, but iPads don't have vibrations, but iPhones do. And so we also became really interested in this understanding of, well, are bigger screens better? Like, that's an assumption we made, but maybe they're not. And we have more work to do here also, but we started with a sort of a simple study looking at a pattern recognition task. So the image that I'm showing has a sort of a grid with certain targets in certain grid squares. So the black squares make a pattern, basically. And then the empty squares, nothing happens. And we asked, and we displayed these grids. They were varied in size, and they were varied across a phone platform that was roughly between a 5 and a 6 inch screen, and a tablet platform, which was between a 9 and a 10 inch screen. And we just wanted to see, if participants were randomly assigned either a tablet or a phone, how did their performance in pattern recognition and their exploration times vary? And so what we found was the pattern matching accuracy, neither device type nor pattern density was a significant contributing factor to accuracy. So in some ways, that was kind of good news for us, because what it suggests is that even the smaller screen size, the people, users' performance isn't necessarily suffering from that. But what we did find was that tablet-sized devices were more useful in situations where the accuracy was most important. But phone sizes, the smaller screen sizes, are quicker. They're quicker to explore. So there's sort of this trade-off. And we have more to look at here in terms of how does this scale as the information you are presenting and the density of that information gets more complex. And I imagine then that we're going to see some advantages on the tablet size. But one of the most interesting findings from this study was the notion of white space. And we see this even in our graphic studies. So bigger screens aren't always better, in the sense of it really does depend on the density of information that you're presenting, because white space is sort of it's not good in touchscreen space. It's like lost in touchscreen space, right? When I have no feedback and I have to go with no feedback for a long time, that's super confusing, because I don't know if I'm still in the active area of the screen, if I've messed something up, if I've completely just lost where I'm at. None of that is clear to me anymore, right? So that was a really interesting finding from this. And inevitably on smaller screen sizes, you have less white space. And then we took this a step further, and we have what's called a scanning laser Doppler vibrometer in our lab. And what's cool is this is a non-contact way to measure vibrations on a surface. So it shines a laser beam down, and then we can measure what's happening on screen without touching the screen. So without impeding the dynamics of the screen. And we're starting to look at, and I'll show on this next slide, we're starting to look at various devices. So one of the important parts of this work that we see is, how do you keep this consistent across devices? How do you keep the feedback and all of the guidelines that we're establishing across hardware platforms, both Android and iOS? That's really, really challenging to do, because the way they sort of create vibration feedback is different. and the sizes matter, whether or not you have a battery pack on matters. All of this stuff comes into play when you're generating vibration feedback. And so we've measured sort of the iPhone 11, the Samsung Galaxy Tab S3, the Motorola Z Play, and then the Z Play with a battery pack, just as an initial sampling. And what I'm showing on the screen here is there's animations that show sort of the vibration amplitude that occurs with each of these different devices. And then on the left is a plot where, so my velocity is on the y-axis and frequency is on the right. And what you can see is this was all devices where we were asking the device to play a vibration of 50 hertz. And we can, and this is what's so exciting is, so iPhone, Apple has recently released Core Haptics, and Core Haptics has made some tremendous leaps in terms of what you can do with vibrations and haptics on iPhone platforms, and they kill it. So you can see on this graph, like 50 hertz is 50 hertz. Like it is crisp, it is clean, it comes out as 50 hertz. Android doesn't do as well with that. And if you have a battery pack on, that also affects it. And the screen size also affects it. That's all I can say right now. We're just getting into these studies, but there's lots of interesting stuff that I think is going to come out of this, looking at how do we ensure that the vibration experience is the same across hardware platforms, because that's really, really important. And then as a team, and this is work that's done in collaboration with Andy Stefik and Derek Smith and Nick Giudici and all of their great students, we've sort of been able to run enough studies and sort of develop the vibration library enough where we can get into setting out some perceptually based guidelines for how to render these graphics. And so we just had a paper accepted that where we go through all of these different guidelines, from how wide should the lines be, at what angle should the lines be, how do you mark different points of interest, what should you do, you should provide a global verbal description at the beginning, all of these things. And we've done this for how to represent graphical elements, how do you go about assigning feedback to these diagrams, what hardware adaptations can you make that are very simple, that make a world of difference in exploring the touchscreen, and then what exploration strategies and user strategies can we employ that help individuals go through and explore these graphics. And then the last part that I'll touch on is what we're doing, what we've done with sort of more complex static like diagrams, as well as where we're moving into dynamic content. So we've done 2 comparative studies so far where we've taken, in the first study, we took relatively simple graphics. I'm showing them on a screen. It was a number line, a bar chart that had 4 bars, a table that had 2 columns and 5 rows, pie chart, very simple map, and a line graph. And we did a comparative study where we looked at individuals felt and heard on the touchscreen and felt these graphics in embossed form, variants of them. And we asked questions about them. And we looked at the percentage of the correct responses across the embossed graphics and the tablet graphics. And usually our studies run somewhere between 10 to 12 participants, and on the high end, maybe 22 to 25 participants. But what was kind of promising from this was, the percentage of correct responses was quite good between both tablet and embossed graphics. And while the tablet is slightly lower, 81% compared to embossed graphics, 87%, from a statistical standpoint, although our sample sizes are low, it wasn't significant. But what's more was, these were individuals who use embossed graphics or have been trained on embossed graphics, and they had 20 minutes of training with the tablet. So that was kind of exciting. We feel like there's room for growth in a situation like that. And then the last study that we looked at has dug deeper into the bar charts and the geometry figures and how do we represent those. And so we did a variety of bar charts and a variety of sort of trig or geometric figures, and we rendered them again in embossed form and on the tablet form. And we asked various questions, and I'm listing these questions. So it could be anything from how many bars are on the graph, what's the title of the graph, how many boys selected grain products, what group selected more milk products. The questions were sort of scaled from, can they extract information from the graphic, to can they make inferences and read data from the graphic. And again, these are some heat maps sort of showing where individuals spend time. Anytime you see that yellow, it means they spent a lot of time there. These get a little bit messier the more complex the graphics get, just because people are spending a lot of time going up and down and going around and exploring the images. But they're a little bit clearer on the more well-defined things, like these geometric shapes. But what did we find here? Again, we really didn't see a lot of difference between the embossed image and the touchscreen images. Whether you look at it from, if you break it out overall, if you look at it purely at the geometry, if you look at it purely at the bar chart. So these were all really, really encouraging findings. Of course, there's still more work to be done, but these were encouraging findings. And here's a little video that just sort of shows the experience of the users. This is a video. We work very closely with Kevin Hollinger and his students at Francis Hall, and this was one of his students exploring a bar chart.
One more in there.
Loading flowers in the garden bar graph.
Oh, it's a bar graph. Yes.
Complete.
So find the X and Y axis.
Flowers in the garden.
Oh,
Daisy, tulip, rose, lily.
that's all.
Daisy, tulip, tulip, daisy.
Here you go.
So that was Olivia running her finger over one of the bars.
11.
11.
Good job. So 11 daisies
Daisy,
in our garden.
tulip, rose,
Lilies were there compared to the tulips.
rose.
Rose smell like pool water. That's why I like rose.
Daisy, tulip, rose, lily,
Oh, no.
lily. 8.
8 lilies.
Wow.
So how many more lilies are there than tulips?
Tulips has 2.
Two what? Two more? Two less?
2 more.
Two more. Yeah, that's
Good
right.
job.
Nice job. Cool.
And so this was work that was
Right
done, oops, sorry. This was work that was done in connection with my startup. So one of the most important things that I do in my lab is that I do not want anything that we work on to stay in the lab. And so I started a startup called Vital. And what we've been working on, most of the research has focused on the student side. How do people interpret and perceive these graphics? What we've worked on the company side is how do we create them in a way that, that's easy, right? Like, how do I make these multimodal graphics? And so we've sort of set up an architecture and an interface in order to be able to do that, where you can upload an image, add audio, add vibrations, add alt tags if you'd like, and then save it and send it out to the student's tablet. So this is just a snapshot of the interface, where you can see we kind of have various tools. It looks kind of like a paint environment, and you can upload an image, and then the OCR, we have some automated tools built in to help so that you don't have to find all the text. All the text will be found and it'll be read. And then you can apply vibrations, sounds, whatever you would like to the image. And what's cool is that this was the initial interface we started, and you can see some renderings of adding vibrations, sort of painting them on, and then it gets sent out. In our latest efforts, we're actually looking at making even that application of the feedback a little bit more automated. So we have some wizard tools where your data goes in and then it pops the graphic out using the guidelines that we've developed and allows you the ability to edit it. So we're getting there on the automation side. That is not a trivial problem, but we're getting there. And so I'll close with what's next. Right now, we're also working with Emily Moore and her team at the PhET simulations to look at how do we expand what we've done in sort of the static graphics space to dynamic content. So things like simulations. So this is an example of 2 simulations, John Travoltage, and then balloons and static electricity. And we're testing out various what we call haptic paradigms, where we're using vibrations to represent different objects or different interactions, and looking at if and how that helps sort of not only the access, but also the experience of the simulation. And in collaboration with Andy Stefik and that whole group, we're looking at how do we expand this out to even more complex data representations, like very dense scatter plots or bar charts with lots of different categories and data to be shown. And we're looking at different layering and sort of categorical techniques to drive that. And then there's always the question that comes up is like, yeah, but it's still vibrations. And that's true. It's still vibrations. And the drawback of vibrations is that there's no intuition behind it. Okay, so we want to be very careful to not just start, you don't want to assign 5 or 10 vibrations to something. Nobody wants to remember that. And so there's always discussions in our lab about how do we add another dimension to the touch surface. And so some of the things that we're looking at are these very small little touch bots that can drive to important parts on the screen, or sort of this handle attachment where some force feedback could be also provided to the user. And so I'll go back to the question that I posed at the beginning, which is why is the haptic channel underutilized in technology? And that's because we just can't capture the richness of human touch. Right? And one of the best examples I have of that is with, I work a lot with individuals with disabilities, and more recently with deafblind individuals, and particularly pro-tactile deafblind individuals. And if anyone has ever seen the PT language, it's incredible. It's a purely touch-based language. And when I look at that as a haptics researcher, I'm like, that is incredible. That's mind-boggling. How are they doing so much with touch, and in technology we're doing so little? And the difference is that it's deeply rooted in haptic intuition. And that, as well as many other examples, illustrates that we as humans have tremendous haptic capacity, and we need to do better with our technologies. But it all starts with learning from those who know touch best, because successful digital transformation is not about the technology at all. It's about the people. And we've been really, really fortunate to work with pioneers in touch. And so with that, I'll stop. Lots of people to thank, all of my collaborators. This is a picture of my lab on the right, lots of great grad and undergrad students. I'm also a mom to 3 boys, twins who are 6, and then William, who thinks he's a triplet with them, who's 3. And our work's been funded most extensively through the National Science Foundation. So with that, I will take questions.
All right, we don't have like a clapping procedure, but
that's okay.
Jazz hands, clapping.
Yeah, right.
For you. But thank you a ton, Jenna. That was always awesome, and it's even interesting for me too, just because I see part of the work that you do just because we collaborate, but I haven't seen you talk about the whole thing, the vision as you see it across the board. So that's really fascinating. Sure. There are a few questions that I noticed in the chat, and I'll ask those first. But if anyone has questions for Jenna, I would encourage you to just dump it wherever you want. Like if you want to dump it in Zoom and that's easier for you, dump it there. If you have a question, you can put it on Slack and I'll look for it there too. The first one was Pranav. He wanted to know, he thought mobile phones had a single motor and that vibrated. Does that single motor, I'm reading into it, but does that single motor impact anything? Does it have any impact having a single motor in these devices, or is that true that some of them don't have single motors, that there's multiple motor tablets, or?
No, so that's true. Most phones and even most tablets only have a single actuator, but you can command different vibrations and different frequencies on that single actuator. Now, in terms of the impacts of that single actuator, I think the trick is, and that's some of the stuff that we're starting to look at, is the bigger your screen gets, depending on where that actuator is placed, you can have effects where a vibration feels really strong, sort of localized or centralized around the actuator, and then it feels more faint on the other edge of the screen. Now, sometimes they place actuators in sort of more strategic places to minimize that, but it kind of depends on the structure of the hardware. You don't see those effects as much on the smaller screen sizes as you do on the larger.
I hope that answers Pranav's question.
Yes, because I was wondering how you created the effects just with one motor.
Yeah, you can. So you can create, you can change, you have a little bit more flexibility in Android than you do in iOS, although iOS has gotten a little bit better with that in Core Haptics in their recent release. But you can change, you can create, and Stefik can probably talk to this as well, because Stefik's team has created an open vibration library, which we use in making these graphics. But you can tune the parameters so that you can create various patterns of known frequencies that you'd like, and intensities as well.
Yeah, that's actually for anybody here. That's actually built into Quorum, so you actually get it on auto magically if you're using Quorum. And then Jenna's team, I think you use the plugin version, the Java version, right?
Right.
Yeah, because you connect it right in. Yeah, if I recall. So.
Yep.
Let's see. So Adam Stockhausen has a question. It is, does the Vital graphic editing environment automatically assign different default vibration and sound elements to an uploaded graphic? Oh, that's a good question. Because I know animation's hard.
Yeah. So when we first released the Vital Content Creator, it did not. And that was partially because we were working with teachers and they really wanted to have, like, they felt some students would like certain feedback and some students wouldn't like certain feedback. So they wanted the flexibility to assign their own feedback. But then once they started going through the process and once we were going through the process, it was like, you know what, it would be much easier if we would just assign some of these for you. And if you want to change them, you can. So in the latest release of the Vital Wizard, it does assign default vibrations and sounds, and then gives you, now we only have the wizard built out for like standard sort of organizers like bar charts, line charts, tables. Can't remember if pie charts is in the latest release or not. But some of the more, it's like if you upload a photograph or some very sort of detailed science diagram that's kind of niche, we don't have the wizard for that. But for standard representations, we do, and it does assign the defaults.
Thank you for that. Actually, I've got a follow-up question regarding that. Does it also, it looked like it, I wasn't certain if this was true, but does it also like automatically read the text that's on a graphic, even though it might be in like JPEG format or whatever it might be?
Yes, it does. So you can run the OCR tool and it'll find it all and then read it. Now, sometimes, like, you know, OCR is not perfect. So sometimes you'll find a little miss, but the good thing is you can edit it. And you can also, like what we often do with the graphics is we add a text box that gives a global description of the image, so that when the image shows up on the screen, they can double tap anywhere on the screen and always get that overview. So.
That makes sense. You know, one thing I had forgotten to mention, whenever you, for anyone that wants to ask a question, if they are using their voice, if you can, and you don't have to, but if you can identify yourself first so that anybody that doesn't know you can hear your name, that'd be great. That was Adam Stockhausen talking. The previous person was Pranav Lal, who lives in India somewhere, to the best of my recollections. So, where do you live, Pranav?
New Delhi, India.
Delhi. Okay, great. There is 2 more questions. One is, following my own rule, this is Stefik. Have you worked or heard of a team at Microsoft working on VR and haptics? I used a white cane on a very clunky device to find the crosswalk. That's from Leslie Wilbacher. I hope I'm saying your name right.
Yep, so I've heard of, and there's multiple teams at Microsoft and other places who are working on sort of variants of haptics and VR or whatever. I have not worked specifically with that team. There's been a lot of work on sort of various iterations of canes. We haven't really gone down that path in our lab, but there's lots of stuff out there for sure. So I can imagine that some of the things you've worked with have been clunky though.
Yeah, I mean, this isn't Jenna's story, but I remember one of the collaborations that we had. I remember we had done an experiment and some of the haptics weren't feelable, right? And I forget exactly what it was, but Jenna started babbling on about butterfly wings and like somebody's flapping butterflies on a magic device, and we're all like, what is this craziness? And that's where this like laser Doppler vibrometer stuff came from, which ended up being crazy helpful for like any possible things. It just amazes me that observation came from butterflies. That just blows me away. But in any case, I think the observation there is that it's really easy to get haptics wrong. Would you disagree with that?
No, it's really easy to get it wrong, but okay, it's not easy to get it wrong. Like we have haptics embedded into all kinds of things. It's just really easy to not use it appropriately, or to use the wrong signals, or to just make some arbitrary mapping or sort of symbolic representation that really has no meaning. And the other thing that you have to be really careful of with vibrations is this fatigue effect that happens over time, where like if something's going to vibrate on your finger constantly for extended periods of time, you're going to experience fatigue. Like it's not going to feel the same, and it's probably not even going to feel pleasant. And so you want to use these in a way where it complements the representation, but the purpose isn't to make like every image have vibrations everywhere. That is not the purpose. The purpose is to infuse these in the right spot where they add an additional layer of information.
Yeah, that makes total sense. I shouldn't use the word babbling. What I meant is I thought that
Oh, I babble.
Well, I babble too. I was going to say, I thought that butterfly insight was just, it blew my mind. It's totally amazing. Totally amazing.
Yeah.
So there's one more question here, which is from Tyler Linder. He says, do the phones have a calibration method? Do you notice any problem as a phone devices as they age? That's a good question.
So, yeah, that's a good question. So, Tyler, I'm not exactly, do you mean a calibration method in terms of sort of the vibrations associated with, or which ones you use?
Yeah, so this is Tyler, but yeah, that was the question is in the frequencies, if you're training somebody for a specific frequency means a specific item, how do you know that between devices you can actually get similar results? Or is it just kind of like as the device age, you just kind of have a learning curve with it?
Yeah, so that's a good question. So we actually don't try to have representations where like someone has to know frequency 50 hertz means this all of the time. Instead, what we try to do is just to have distinct vibrations. So like, for example, if I have a bar chart and I have two categories, I have boys and girls. The boys vibration might be like this sort of buzz, whereas the girls vibration is going to be something that's more like discrete units, like zzz, 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 or something like that. And so the purpose isn't for them to remember that 50 hertz means boys. It's just to remember constant means boys, and this more bumpy pattern means girls. And then in the next graphic, it could be something different. So we try not to have to do something where people have to know the frequencies of the vibration and those always mean something. Now you could, and if that was the case, then yeah, there would have to be some sort of training procedure. And there's been a lot of work in haptics that shows that people can remember crazy numbers of vibrations and can distinguish frequencies at very low thresholds. In this context, I'm not necessarily in favor of doing that just because I think we're trying to make this easier. And so if there's an extensive sort of cognitive workload associated with just remembering the mappings, then we're kind of doing a disservice. Do we notice any problems as phones or devices age? Depends. I mean, sometimes, so the biggest problem with vibrations is that it's going to tax your battery more. So your power, your battery's not going to last as long. We tend to just have the devices plugged in while we're using them just because it's easier. But I'd say like, if you're using a device where your battery only lasts 20 minutes anyway, then that's a little bit of a problem. The other kind of, I guess, the other sort of barrier that we have with using vibrations, and this is more so on the Apple side than the Android side, is when we put apps up into the store, there are certain criteria that we have to meet and certain things that we can't do. So for example, for a long time, Apple would not let us run a vibration for longer than like 3 seconds because they were worried it was gonna really hurt the battery performance of users. And so we had to kind of do some workarounds there to make sure that we weren't employing that. But other than that, not a ton.
Thank you.
Sure, thanks for the question.
Okay, these are all great questions. Any other questions from folks? Not seeing anything else on Slack.
I think I went into the 10-minute buffer. I'm sorry for that.
Oh, you're fine. There's no rules really. I do have one more question for you that I don't know if people are interesting or not. And I think I know the answer, but I'm not positive I know the answer. I know that there is some, different humans have different thresholds for what they can touch. For example, if you have diabetes or something like that, is there any research, showing that the standard deviation is really large between people, or is it mostly a disease related, or that causes lower thresholds, or do you have any idea there?
Yeah, so there's a lot. So disease does impact sort of fingertip. We're talking mostly about fingertip perception here. But the other thing that really, impacts it, and we have this that just sort of naturally shows up in our studies, is, I mean, even if somebody's like sweating and it makes your fingers really sticky, that impacts perception. And so there is literature out there. I don't know that at the end of the day, I mean, it's a little bit of a free-for-all, and we try to just let these variables happen in our studies so that to the extent that we can, we account for it. But I mean, everyone's perception is a little bit different. And what's even harder is that everyone prefers different things. I mean, like in our line following study, it was pretty amazing to us that most people prefer the vibrations, sort of tracing the vibration lines over the auditory lines, but sort of people prefer different vibrations. And so I think that's where it becomes a little bit tricky. Like, we want to automate things to assign stuff, but we also want to recognize that everybody likes different things. Just like we like to go through our phones and pick out different ringtones or different vibration patterns. We want to be able to give people the ability to do that. So when you have these discrepancies, or what feels different to one person doesn't quite feel different to the other, you can sort of personalize it or account for it. But certainly there's factors that affect it, including time of use, right? Like, that's not a long-term thing, but a short-term thing.
That makes sense. It looks like there's one more question from Sarah Larkin. She asks, some tactile graphics have keys for the different textures or lines. Do you ever have a need for keys related to the vibrations?
Yeah, so Stefan, we've iterated on this multiple times in terms of like, do we have legends? Do we not have legends? We don't really need legends, but maybe we need legends. And the same is true for keys. So the cool part about it is that like when we're doing a graphic, if we have a legend, usually it's sort of there once as okay, this is what this is, and this represents boys and this represents girls, and then it doesn't have to be continuously revisited. But the other thing that we started looking at is just embedding it in the graphic. So for example, while they're feeling the bar that represents boys, the first time they go onto the bar, it just says boys. And so there's no longer the need to sort of move over to the key. Now, sometimes you explicitly want to teach students like how to use a legend or a key. And in that sense, then yes, have it. But if we're trying to really optimize when and where and how they have to extract information, we can also do some layering with other feedback to just give them the information sort of in real time while they're using it. That's a great question.
Yeah, I thought so too. Well, I'm not seeing anything else. So let me just say, hey, I super appreciate it. I think the work that you've done over the last, whatever you said it was, 8 years is just ridiculously fantastic. So I could not thank you enough for not just coming and talking to all of us, but also just like for doing the amazing work that you do. So thank you as one scholar to another for doing great work and for coming and talking to all of us. Super appreciate it.
Thanks for being a great audience, and thanks for having me.